Following John Barrow's lecture on zero, the nothingness number, and Raymond Flood's lecture on I, the imaginary number, let's now look at two other mathematical constants, pi, the circle number, and e, the exponential number, before combining them all into what many have claimed is the most beautiful theorem in mathematics. One person featuring throughout this story is the Swiss mathematician Leonhard Euler, who spent most of his life in the imperial courts of St. Petersburg and Berlin. The most prolific mathematician of all time, Euler published over 800 books and papers in over 70 large volumes. Ranging across almost all branches of mathematics and physics at the time, these amounted to about 1/3 of all the maths and physics publications of the 18th century. So first we meet the number pi, which, as we learned at school, is a little bit more than 3.14 and a little bit less than 22/7. It arises in two ways. First, as the ratio of the circumference of a circle to its diameter. That is, pi is c/d, so c is pi d or 2 pi r, where r is the radius. This ratio is the same for circles of any size, from a pizza to the moon. But it's also the ratio of the area of a circle to the square of its radius. Pi is a over r squared, so a is pi r squared, or pi d squared over 4. And this ratio is also the same for all circles, as Euclid proved in the 3rd century BC. We can never write down pi exactly. Its decimal expansion goes on forever. But if my 5 decimal places weren't enough for you, here are a few more. Or if that's still not enough, here is even more. And amazingly, pi has been memorized to over 100,000 decimal places. What a way to spend a life. And calculated to over 20 trillion. But even that's only a beginning, and there's still a long way to go. But if you happen to live in the Karlplatz area of Vienna, and you need the first 478 digits of pi, don't worry. You can always consult the walls of your local metro stop. But why does the same number pi appear in both the formula for the circumference and the formula for the area? One way to answer this is to take two circles of radius r, one shaded, as here, and the other unshaded, and to assume that each has circumference 2 pi r. We next divide each circle into a number of sectors, here, first 4 above and then 9, and then rearrange these sectors into a shape that looks a bit like a parallelogram. And as the number of sectors increases without limit, this parallelogram increasingly resembles a rectangle with sides of length 2 pi r and r, and with area 2 pi r times r, which is 2 pi r squared. So the combined areas of the two original circles must also be 2 pi r squared, and so each one has area pi r squared, as we'd expected. And we can then reverse this argument to show that if the area is pi r squared, then the circumference must be 2 pi r. Such ideas, such an approach, quite old. On the right, they appear in a Japanese treatise from the year 1698. When did people start to measure circles? Several early civilizations obtained estimates for the circumference or area of a circle, and although they had no conception of pi as a number, their results yield approximations to its value. Let's begin with the Mesopotamians, who wrote their mathematical calculations on clay tablets using a number system based on 60 that we saw in John Barrow's lecture. One of these tablets, dating from about 1800 BC, gives the ratio of the perimeter of a regular hexagon to the circumference of the circle surrounding it. It gives it as the sexagesimal number 0.5736. Now, if the radius of the circle is r, then each side of the hexagon also has length r, and so this ratio is 6r over 2 pi r, or 3 over pi. And that's equal to 57 over 60 plus 36 over 3600. That's 60 squared. After some calculation, this gives a value for pi of 3 1/8, or 3.125 in our decimal notation. A lower estimate that's within 1% of the true value. Around the same time, an Egyptian papyrus included the following problem. This is problem 50 of the Rhine Papyrus. Example of a round field of diameter 9 ket. What is its area? And the answer is given in steps. Take away 1/9 of the diameter, which is 1. The remainder is 8. Multiply 8 times 8, it makes 64. Therefore, it contains 64 cetat. That's a measure of land. From this calculation, it seems that they found the value for the area of a circle of diameter d by reducing d by 1/9 and then squaring the result, as you can see. And this method was probably discovered by experience. Other explanations have been proposed, but none seems to be supported by historical evidence. And in terms of the radius, this area is 256 over 81 r squared, which corresponds to a value for pi of 256 over 81, which is about 3.160, an upper estimate that's also within 1% of the true value. An important new method for estimating pi was introduced by the Greeks and would be used for almost 2,000 years. It involves approximating a circle with polygons. But although it's often attributed to Archimedes, the method can be traced back a further couple of centuries to the Greek sophists Antiphon and Bryson. Their aim was to obtain better and better bounds for pi by repeatedly doubling the number of sides of a regular polygon within or surrounding the circle until the polygons eventually became the circle. So Antiphon first drew a square inside the circle of radius r and found its area, giving a rather poor lower bound for pi of 2. He then doubled the number of sides, giving an octagon, and finding the better bound of 2 root 2, 2 times root 2, or 2.828. Bryson's approach was the same, except that he also considered polygons surrounding, that is, outside the circle, and this yields upper bounds of 4 for the square and about 3.32 for the octagon. Archimedes became interested in circular measurement around 250 BC, proving that a circle of radius r has area pi r squared, and that a sphere has surface area 4 pi r squared and volume 4/3 pi r cubed. But unlike Antiphon and Bryson, who'd used areas, Archimedes worked with perimeters. He first approximated the circumference of a circle by the perimeters of regular hexagons, drawn inside and outside the circle, and carried out the appropriate calculations to give the lower and upper bounds for pi of 3 and 2 square root of 3. So in our decimal notation, pi lies between 3 and 3.464, as shown below on the right. He then doubled the number of sides of the polygons, replacing the hexagons by dodecagons, and getting the better estimates of 3.105 and 3.215. And 3 more doublings to polygons with 24, 48, and 96 sides then gave ever closer values, with his bounds for polygons with 96 sides presented eventually as 3 and 10 over 71 and 3 and 1 over 7, or in decimal notation between 3.14084 and 3.14286, so giving pi correct to 2 decimal places. And as Archimedes expressed it, the circumference of any circle exceeds 3 times its diameter by a part which is less than 1/7, but more than 10 over 71 of the diameter. What was happening elsewhere? In China, an early value for pi was given by Zhang Hong, inventor of the seismograph for measuring earthquakes. This was the square root of 10, which is about 3.162, which is a useful approximation for the time. But around the year 263, in his commentary on the Chinese classic 9 Chapters on the Mathematical Art, Liu Hui used inscribed regular polygons to approximate pi. And starting with hexagons and dodecagons, as you can see here, he developed simple methods for relating the successive areas and perimeters when one doubles the number of sides. And for polygons with 192 sides, that's twice 96, he obtained lower and upper bounds of about 3.141 and 3.143. And 4 more doublings led to polygons with 3,072 sides and to his approximation of 3.14159. Even more impressively, around the year 500, Zhu Zhongzhi and his son doubled the number of sides 3 more times, extending their calculations to polygons with over 24,000 sides and obtaining estimates that give pi to 6 decimal places. They also replaced Archimedes' fractional approximation of 22 over 7 by the more accurate 355 over 113, which also gives pi to 6 decimal places. And as we'll see shortly, this latter approximation wasn't rediscovered in Europe for another 1,000 years. After this, everyone got in on the game. In Italy, in a geometry book of 1220, Leonardo of Pisa, known to us as Fibonacci, cited earlier calculations and used polygons with 96 sides to give pi as 3.141818. Then in 1424, the Persian astronomer Al-Karshi, who was working at Ulugh Beg's observatory in Samarkand, used polygons with over 800 million sides to find pi to a remarkable 9 sexagesimal or 16 decimal places. And this remained the best value for almost 200 years. Meanwhile, European mathematicians from several countries were using similar methods. In 1579, the French lawyer and mathematician François Viette, whom we'll see later, used polygons with over 393,000 sides to find pi to 9 decimal places, while 6 years earlier, the German mathematician Valentine Otto had proposed the fraction 355 over 113, and as we saw earlier, this value was already known to Zhu Zhongzhi 1,000 years previously and gives pi to 6 decimal places. In 1585, the Dutch cartographer Adrian Antonis obtained the same value by accident. He found the lower and upper bounds of pi to be 333 over 106 and 377 over 120. He then averaged their numerators and their denominators and got the same result. Also in the Netherlands, Adrian van Rumen used polygons with 2 to the 30 sides, that's over 1 billion, to find pi to 15 decimal places. But best of all was Ludolf von Keulen, who used polygons with over 500 billion sides to find pi to 20 decimal places. His upper and lower estimates are shown here below his portrait in his book on circles. But not content with this, he then used polygons with 2 to the 62 sides, which you can see written out there, to find pi to 35 decimal places. And he asked for this latter value to appear on his tombstone in Leiden, and for many years pi was known in Germany as the Ludolfian number. Up to this time, most estimates for pi had been bounds on its value, but new approaches were taken by François Viette and John Wallis, who obtained exact expressions involving products of infinitely many terms. In 1579, Viette showed that we can find 2 over pi by multiplying the cosines of pi over 4, pi over 8, pi over 16, and so on forever. Here the angles are given in radian measure, where pi corresponds to 180 degrees. So that the first term is the cosine of 45 degrees. And noting that this is 1/2 of root 2, he was then able to rewrite his result in terms of horrible expressions involving successive square roots, as you can see. Later in 1656, another infinite product was presented by John Wallis, the civilian professor of geometry at the University of Oxford. And it expresses the number 4 over pi as 3 over 2 times 3 over 4, times 5 over 4 times 5 over 6, and so on. The pattern should be clear. And below you can see his lower and upper estimates for 4 over pi. He wrote 4 over pi as a small rectangle. But unfortunately, although such products have theoretical significance, they converge very slowly to pi and have no practical value. But a new and highly productive method for estimating pi, which came to be used extensively throughout the 18th and 19th centuries, involved the inverse tangent function, usually written as tan to the minus 1x or arc tan x. If y is tan x, turning it round, then x is tan to the minus 1y. For example, tan of pi by 4 is 1, so tan to the minus 1 of 1 is pi by 4. Tan of pi by 6 is 1 over root 3, so tan to the minus 1 of 1 over root 3 is pi over 6. And we can combine different values of tan to the minus 1. For example, as you see in the picture on the left, if you add tan to the minus 1 a half near the bottom, and tan to the minus 1 a third just above it, you get pi by 4, 45 degrees. This can then be proved by simple geometry. And in general, we can use the formula at the bottom to combine inverse tangents. And if you take that formula and put x as a half and y as a third as before, then on the right, x plus y and 1 minus xy are both 5, 6. So that gives you tan to the minus 1, 1, which is just pi by 4 as before. Now, many mathematical functions can be written as infinite series. For example, we can write tan to the minus 1 of x as the infinite series shown here, using only odd powers of x and with odd numbers in the denominators. This result was already known to Madhavar in 15th century India, but is usually named after the Scotsman James Gregory, shown here, who rediscovered it 300 years later. If we now let x equal 1, we get a series expression for pi over 4, a result also due to Madhavar, but usually credited to Leibniz. And this is one of the most remarkable results in the whole of mathematics. By simply adding and subtracting reciprocals of whole numbers, 1 over whole numbers, we get a result involving the circle number pi. Unfortunately, the Leibniz series converges exceedingly slowly, and we cannot use it to find pi in practice. For example, if we calculate the first 300 terms, we get pi to only 2 decimal places. If you want 5 correct decimal places, you have to calculate 500,000 terms. But you can still use Gregory's series to estimate pi if you substitute values other than 1. And remembering that tan to the minus 1 a half and tan to the minus 1 a third add up to pi over 4, we can substitute x as a half and x as a third into the series for tan to the minus 1, giving these two series shown here. And because of the increasing powers of 2 and 3 in the denominators, these series converge much faster, yielding good estimates for pi. In fact, in 1861, a certain W. Lehman of Potsdam used these very series to find pi to 261 decimal places. So the search was now on to find new 10 to the minus 1 identities where the series converge even faster. And in 1706, John Machin used the addition formula several times over to prove that pi is 16 times 10 to the minus 1, 1 over 5, minus 4 times 10 to the minus 1, 1 over 239, and then wrote out the corresponding 2 10 to the minus 1 series, as you can see here. Now, both of these series converge rapidly because of the powers of 5 and 239 in the denominators. For example, we get the value 3.14 from just the first 3 terms of each series. Moreover, 5 is an easy number to divide by, so calculations are simplified, and Machin was thereby able to calculate pi by hand to 100 decimal places, a great improvement on anything that had gone before. And incidentally, John Machin later became Gresham Professor of Astronomy for over 40 years. 1706. That was a good year for pi. As well as Machin's result, a Welsh maths teacher called William Jones wrote a new introduction to the mathematics, in which he introduced the symbol pi for measuring circles. And in the upper extract here, halfway down, you can see Machin's series, and then just below it is the first ever appearance of the symbol pi in the penultimate line. And the lower extract from the same book includes Machin's value in full. As he said, true to above 100 places as computed by the accurate and ready pen of the truly ingenious Mr. John Machin. But it was Euler who popularized the use of the letter pi, first in a work of 1737, and then in many later writings, so that it soon came to be used universally. And one of Euler's many results involving pi was this 10 to the minus 1 identity, which enabled him to calculate 20 decimal places of pi in 1 hour. It was used again in 1794 by the Slovenian Juri Vega to calculate pi to 136 decimal places, and for many years, this was the most accurate value known. But there were persistent references in the literature to an earlier and more accurate value seen by the Hungarian Baron von Zach while visiting Oxford's Bodleian Library in the 1780s. Where was this reference? No one could find it until it was eventually located in 2014 by BSHM member Benjamin Wardo, and it confirmed that in 1721, a resident of Philadelphia, we don't know their name, used 314 terms of the series for tan to the minus 1 over root 3, you can see here, calculated with great accuracy to obtain pi correctly to 152 decimal places. Actually, he calculated 154, but he got the last two wrong. This was indeed the world's most accurate value of pi for over 100 years, even though it was largely unknown at the time. But most notorious of all was the value obtained by William Shanks, who in 1873 used Machin's formula to calculate pi to an impressive 707 decimal places. And these were later inscribed in a ceiling frieze in the pi room of the Palace of Discovery in Paris, where you can still see them. But unfortunately for him and for the Palais, it was later found that only the first 527 of these decimal places were correct. But they weren't going to repaint the ceiling. The 20th century saw a number of discoveries about pi, many of them completely bizarre. Here are three of them. In 1914, the Indian mathematician Ramanujan found several remarkable exact formulas for 1 over pi, including this infinite series in which strange numbers such as 1103 and 26,390 seem to appear from nowhere. And we think that's ridiculous. Many years later, in 1989, David and Gregory Chudnovsky of New York produced a similar but even more complicated result with these even larger numbers here. Such series converge extremely rapidly and form the basis of some of today's fastest algorithms for calculating pi. My third example is a very different type of result. Discovered in 1995 by David Bailey, Peter Borwein, and Simon Plouffe, it caused a great deal of surprise. It's a much simpler series, and its importance is that if we work in a base 16 number system rather than in base 10, we can then calculate each digit of pi one at a time without having to recalculate all the preceding digits first. It's quite remarkable. By this time, computers had entered the scene, and it was now possible to calculate pi to a much greater accuracy, as you can see from this table here. Briefly, the first advance was in 1949 when Machin's series was put to good use on the American ENIAC machine to calculate pi to 2,037 places in 70 hours. Machin's series was again used in 1955 to find pi to 3,089 decimal places in just 13 minutes on the Naval Ordnance Research Calculator. Meanwhile, progress has been made in England, and in 1957, a different 10 to the minus 1 series was used on the Ferranti Pegasus computer to calculate over 10,000 decimal places in 33 hours, though not all were correct. Then IBM entered the scene, and the number of decimal places rose rapidly, while the calculation time plummeted. 1973 saw 1 million decimal places for the first time, reached in 23 hours on a CDC 7600 machine. And the scene then moved to Japan, where the number of places increased to 10 million in 1983, 100 million in 1987, and over 500 million in 1989. Using very sophisticated 10 to the minus 1 formulas and carrying out their calculations in base 16, the Japanese were able to calculate the individual digits of pi one at a time, as we saw earlier, before translating their results back into base 10. Meanwhile, in New York, the Chudnovsky brothers were developing algorithms for their home-built supercomputers to push the numbers even higher, and in 1989, they were the first to exceed 1 billion places. There was then a frantic race for the Japanese group, with 1 trillion places being achieved in 2002 and 10 trillion in 2011. Since then, the number of calculated places has increased to over 20 trillion. Incidentally, you only need 15 decimal places to be able to measure a couple of inches at the far end of the universe. Let's end our discussion of pi with a simple puzzle that appeared in 1702 in a book on Euclid's elements by the Cambridge mathematician William Whiston. If you haven't seen it before, you may find its answer surprising. The circumference of the Earth is about 25,000 miles. Assuming the Earth to be a perfect sphere, supposing you tie a bit of string of this great length tightly round it. Don't try this at home. We can then extend this string by just 2 pi, that's just under 6.3 feet, and prop it up equally all around. So how high above the ground is the string? Most people think the circumference of the Earth, you only added about 6 feet. Most people think the resulting gap must be extremely small, perhaps a tiny fraction of an inch. But the correct answer is 1 foot. And in fact, you get the same answer whether you tie the string around the Earth, a tennis ball, or any other sphere. For if the sphere has radius r feet, then the original string has length 2 pi r. When you extend it by 2 pi feet, the new circumference is 2 pi r plus 2 pi, which is 2 pi times r plus 1. So the new radius is r plus 1, 1 foot more than before. So that concludes the first part of the talk on pi, and let's now move over to the exponential number e. How fast do things grow? We often use the phrase exponential growth to indicate something that grows very fast. But how quickly is this? This part of the talk concerns the number e is 2.71828, etc. Like pi, its decimal expansion goes on forever. The letter e was first used for this number around 1727 in an unpublished paper of Euler. And its first appearance in print was in 1736 in Euler's Mechanica on the mathematics of motion. And here you can see it. It appears in the penultimate line, and it says where e denotes the number whose hyperbolic logarithm is 1. So that's the first ever appearance of e, just as you've seen the first ever appearance of pi. To illustrate what we mean by exponential growth, let's start with a story about the invention of the game of chess. Some of you may have come across this before. The wealthy king of a certain country was so impressed by this new game that he offered the wise man who invented it any reward he wished, to which the wise man replied, "My prize is for you to give me 1 grain of wheat for the first square of the chessboard, 2 grains for the second square, 4 grains for the third square, and so on, doubling the number of grains on each successive square until the chessboard is filled. The king was amazed to be asked for such a tiny reward, or so he believed, until his treasurers calculated the total number of grains of wheat. This is 1 plus 2 squared up to 2 to the 63, which works out as 2 to the 64 minus 1 grains. You can see the number here, which is enough wheat to form a pile the size of Mount Everest. If you place them end to end, they'd reach to the nearest star, Alpha Centauri, and back again. So let's see how quickly various other sequences can grow. The simple form of growth is linear growth, illustrated by the counting numbers n, that's 1, 2, 3, 4, 5, and so on. Somewhat faster is quadratic growth, involving the perfect squares n squared, 1 squared, 2 squared, 3 squared, and so on. And even more rapid is cubic growth involving the cubes n cubed, 1 cubed, 2 cubed, 3 cubed, 4 cubed, and so on. These are all examples of polynomial growth, since they involve powers of n. But alternatively, we could look at powers of 2 or of any other number. And as we saw in the chessboard story, the sequence 2 to the n of powers of 2 starts off fairly slowly, 1, 2, 4, 8, 16, 32, but soon gathers pace because each successive term is twice the previous one. And the sequence 3 to the n of powers of 3 takes off even more quickly, 1, 3, 9, 27, 81, 2, 4, 3. These are examples of exponential growth where n appears as the exponent. And to compare these types of growth, here are the running times of some polynomials and exponentials when n is 10, 30, and 50 on a computer performing 1 million operations per second. For polynomial growth, such as n to the 5th, such a computer takes 5 minutes when n is 50. But exponential growth, such as 2 to the n, is much greater. When n is 50, the computer would take over 35 years, and would be vastly greater than this, as you can see, for 3 to the n. So in the long run, exponential growth tends to exceed polynomial growth, often by a huge margin. Algorithms that run in polynomial time are generally thought to be efficient, whereas those that run in exponential time normally take much longer to implement as the input size increases and are considered as inefficient. So returning to E, what exactly is this number and how did it arise? In 1683, the Swiss mathematician Jacob Bernoulli was calculating compound interest. Given a sum of money to invest at a given rate of interest, how does it grow? The answer depends on how often we calculate the interest. How much is earned if we calculate it yearly? Twice a year, every month, every day, n times a year, continuously. To answer this, suppose that we invest £1 at the unlikely annual rate of 100%. After 1 year, the amount's increased to £2. But what happens if we calculate the interest twice a year? After 6 months, the amount has increased by 50% to £1.50. And after the second 6 months, this has then increased by a further 50% to 1.5 times £1.50, which is £2.25. Similarly, if the amount is calculated 4 times a year, then every 3 months, the amount increases by 25%, so that by the end of the year, it has become £1 multiplied by 1.25 4 times. That is 1 plus a quarter to the 4th, which is about £2.44. And if the interest is calculated n times a year, then after each period of time, the amount is multiplied by 1 plus 1 over n, so that at the end of the year, it has become 1 plus 1 over n to the n pounds. So this table shows how these amounts increase as we calculate the interest with increasing frequency. And we can also see that as n increases indefinitely, these numbers tend to a limiting value that corresponds to when the interest is calculated continuously. This limiting value of about 2.71828 is the exponential number that Euler called E. The greatest advances in understanding exponentials were made in the early 18th century. After Bernoulli, the main figure in the story was Euler, who investigated the properties of E and of the exponential function e to the x. And in 1748, one of the most important mathematics books ever written, his Introduction to the Analysis of Infinites, brought together many results from his earlier works. And here are some of his main findings. We've just seen that E is the limit of the numbers 1 plus 1 over n to the n as n increases indefinitely. And similarly, we can show that e to the x is the limit of 1 plus x over n to the n for any number x. But as Isaac Newton had already discovered, the number e is also the sum of the infinite series shown here, where the denominators are the factorials, 1, 1 times 2, 1 times 2 times 3, and so on. And more generally, there's a similar series for e to the x, and this converges for all values of x. In fact, these series converge very quickly because the factorials increase so rapidly. For example, the first 10 terms of the series for e already give e to 5 decimal places. Now on the right, you can see the graph of y's e to the x. One of its most important features is that at each point x, the slope of the graph is also e to the x. That is, the slope at any point is the y value. So the curve becomes ever steeper as x increases. The number e is also intimately linked with logarithms. So let's look briefly at these. Since the Middle Ages, ways have been sought for turning lengthy calculations involving multiplications and divisions into simpler ones involving additions or subtractions. And in the 16th century, the German Michael Stiefel and others developed a new method for doing so. This was to turn geometric progressions, whose successive terms have a common ratio, into arithmetic ones, whose successive terms have a common difference. This process was called prosopharesis, from the Greek words for addition and subtraction. Now in 1614, the Scotsman John Napier, 8th Laird of Merchiston near Edinburgh, produced his description of the wonderful canon of logarithms shown here. This important work contained extensive tables of the logarithms of sine and tangents of all the angles from 0 to 90 degrees in steps of 1 minute of arc. Napier's emphasis on these functions arose from his interest in spherical geometry, so that his excellent brief rules, as he called them, could be used by navigators and astronomers. Well, Napier's logarithms originated from this idea of prosopharesis. He considered 2 points moving along straight lines. You can see them here. The upper one, PQ, is of finite length, and the lower one, L0L, is of infinite length, as follows. The upper point moves from P towards Q in such a way that its speed at each point is proportional to the distance that it still has to travel. So it slows down. While the lower point, representing its Napierian logarithm, starts from L0 and travels at constant speed towards L forever. So in successive periods of time, the distances still to be traveled by the first point form a geometric progression, and the distances already traveled by the second point form an arithmetic progression. Well, Napier took 10 to the minus 7 as his successive time intervals, and then multiplied his results by 10 to the 7 in order to avoid the use of decimal fractions, which were still largely unfamiliar at the time. And it followed from his construction that the log of 10 million is 0, and that as n decreases, its logarithm increases, unlike those we use today. And it also followed that log of a times b is log of a plus log of b minus log of 1. So that for each calculation, he had to subtract the cumbersome term log of 1 shown at the bottom. Not very easy. So to the rescue comes Henry Briggs in 1615. Henry Briggs was the first professor of geometry at Gresham College in London, And he heard about Napier's logs and was wildly excited by them. He included in his Gresham lectures, just as I'm doing today, enthusing that Napier had set my head and hands to work with his new and remarkable logarithms. I never saw a book which pleased me better or made me more wonder. But Napier's logs were cumbersome to use, and Briggs wanted to redefine them so as to avoid having to subtract log 1 in every calculation. I myself, when expounding this doctrine to my auditors in Gresham College, remarked that it would be much more convenient that 0 should be kept for the logarithm of the whole sign, that is 1. Briggs twice visited Edinburgh to stay with Napier, and it's recorded that when they first met, they spent the first quarter hour looking at each other in admiration without speaking a word. The outcome of their meetings was that Briggs started to construct logs to base 10, where log 1 is 0, log 10 is 1, log 100 is 2, and so on. Other values he found by interpolation. In order to find these accurately, he calculated the square root of 10, then the square root of that, and so on, eventually taking square roots 54 times, all to 30 decimal places. Since log of 1 is 0, as he demanded, Briggs's logarithms satisfy the simpler fundamental rule, log of a times b is log of a plus log of b. And in 1617, Briggs, while still at Gresham College, Briggs produced this small pamphlet shown here containing his calculations. And 7 years later, after he'd left London to become the first civilian professor of geometry at Oxford University, he followed this with his Arithmetica Logarithmica, an extensive calculation of logs to base 10 of the integers from 1 to 20,000 and from 90,000 to 100,000, all calculated by hand to 14 decimal places. The gap in these tables between 20,000 and 90,000 was later filled by a Dutch mathematician called Adrian Vlak. Now, the fundamental connection between the functions e to the x and log x, where from now on x is the base of the logarithms, is that they're inverses of each other. In symbols, log of e to the x is x, and e to the log y is y. And it follows that if we take x, calculate e to the x, and take the log to base e of the result, we get back to x. Or if we take x, calculate log to base e of it, and take the exponential of the result, again we get back to x. This inverse relationship had been noticed by John Wallis back in 1685 and was developed by Euler in his Introductio with more available machinery by that time. And using it, we can show that the multiplicative law for exponentials, you can see here, and the basic law of logarithms are essentially the same result. And we notice also from the picture that since e to the x and log x are inverses of one another, their graphs can be obtained from each other by reflecting in the line y equals x. Well, before leaving exponentials, let's now change pace by looking at two applications of the exponential function to derangements and to population growth. Around 1710, de Moivre, whom we saw earlier, de Montemort, and others posed the following problem. Given any n letters, in how many ways can we rearrange them so that no letter is in its original position? Or a more popular form of the problem is, if we randomly place the number of messages into addressed envelopes, what's the probability that no message ends up in the correct envelope? Such rearrangements are called derangements. For example, when n is 4, there are 4 factorial or 24 permutations of the 4 letters, but of the 24, only the 9 you can see here are derangements with no letter in its normal position. Well, to investigate this question, let's let d of n be the number of derangements of n letters. So d of 4 is 9. And this table shows the values of dn for all n up to 8. It was around 1779 that Euler became interested in derangements and used a counting argument to show that dn has this value given here. This was a result that de Moivre had actually obtained some years earlier. But unfortunately, this value can be very time-consuming to evaluate for all but the very smallest values of n. But there's a quicker way. Because the expression in brackets is the beginning of the series for e to the minus 1. So d of n is very close to n factorial times e to the minus 1, or n factorial over e. And in fact, for every n, dn is the integer closest to n factorial over e. For example, when n is 8, n factorial over e is about 14,832.9, while the value of d of 8 is the nearest integer, 14,833. And that's true for any value. To end this discussion of exponentials, let's return to exponential growth. In 1798, Thomas Malthus wrote his essay on population, where he contrasted the steady linear growth of food supplies with the exponential growth in population. He concluded that, however one may cope in the short term, the exponential growth would win in the long term, and that there would be severe food shortages, a conclusion that was borne out in practice. So how fast does a population grow? And I'm assuming a bit of calculus here. If n of t is the size of a population at time t, and if the population grows at a fixed rate k proportional to its size, then we have the differential equation dn by dt, that's the growth in population, is k times n. This can be rewritten as dn over n is k dt, which we can integrate to give log of n is kt plus constant, or in terms of exponentials, n is a multiple of e to the kt, where the multiple turns out to be the initial population, n0. So n of t is n0 e to the kt, an example of exponential growth. And in the same way, we can model exponential decay, as for example in the decay of radium, or in the cooling of a cup of tea. We come now, at last, to the equation which regularly tops the polls among mathematicians as the most beautiful theorem in mathematics, namely e to the I pi plus 1 equals 0, or e to the I pi is minus 1. It's remarkable for combining 5 important but very different constants, each with deep mathematical significance, and each with its own story, as we've seen today. These are 1, the basis of our counting system, 0, the number expressing nothingness, pi, the basis of circle measurement, e, the number linked with exponential growth, and I, the imaginary square root of minus 1. It also involves the fundamental mathematical operations of addition, multiplication, and taking powers, and the notion of equality. As one participant in a different poll in Physics World was moved to remark, what could be more mystical than an imaginary number interacting with real numbers to produce nothing? Indeed, at the age of only 14, the future Nobel Prize-winning physicist Richard Feynman had called it the most remarkable formula in math, while the Fields Medal winner Sir Michael Atiyah has described it as the mathematical equivalent of Hamlet's to be or not to be, very succinct, but at the same time very deep. It's even featured twice in The Simpsons and was crucial in a criminal court case. But those are stories for another day. Although we call this result Euler's equation, it was nearly discovered a few years earlier by Johann Bernoulli. As we've seen, the logarithm function log x is defined for all positive values of x, but can it be defined when x is negative? This question caused disagreement between Leibniz, who believed the logarithm of a negative number to be impossible, and Bernoulli, who used the basic property of logs to prove that log of minus 1 is 0. How did he do that? Well, twice log of minus 1 is clearly log of minus 1 plus log of minus 1. By the rule, that's log of minus 1 times minus 1, which is log of 1, which is 0. So twice log of minus 1 is 0, log of minus 1 is 0, and he gave a similar proof that log of minus x is log x for all x. Well, later, around 1702, Bernoulli was investigating the area A of a sector of a circle of radius A. You can see that on the right. It's a shaded area between the x-axis and the line from the origin to the point xy. And he found this to be a squared over 4I times the log of x plus iy over x minus iy. And don't worry about the details and don't worry about what's meant by the logarithm of a complex number. Bernoulli didn't seem to worry. But Euler later observed that if you put x equals 0, then the formula simplifies to a squared over 4i times log of minus 1. But because such a sector clearly has a non-zero area, you can see it's a quarter circle, that shows the logarithm of minus 1 cannot be 0, contradicting Bernoulli's result above. And moreover, since it's a quarter circle with area pi a squared over 4, that area must be equal to a squared over 4i times log of minus 1. And if you stir it around, you find that log of minus 1 is I pi, a complex number. Although Euler wrote down this last result explicitly, he doesn't seem to have taken exponentials at the time to deduce Euler's equation in the form e to the I pi is minus 1. And indeed, Euler often credited Bernoulli with discovering this value for log of minus 1, but Bernoulli hadn't included it in the 1702 paper or in any later work, continuing to insist that log of minus 1 is 0. As we'll see, Euler's equation is a special case of a general result that Euler published in 1748 in his Introductio. This celebrated result relates the exponential function e to the x and the trigonometric functions cos x and sin x. But why should the exponential function, which goes shooting off to infinity as x becomes large, have anything to do with these trig functions which forever oscillate between the values 1 and minus 1? Indeed, there's no real reason why there should be any such relationship. No real reason, but there are complex reasons. Because introducing complex numbers leads to such connections, and realizing this was one of Euler's greatest achievements. And to see the connection, we recall that these functions can all be expanded as series valid for all values of x. So here are the series, e to the x, cos x, and sin x. And what happens if we now allow ourselves to introduce the complex number I, the square root of minus 1, as Euler did in 1737? So we'll take the series for e to the x and replace x by ix, as we see here. We get e to the ix is 1 plus ix over 1 factorial, plus ix all squared over 2 factorial, plus ix all cubed over 3 factorial, and so on. But since I squared is minus 1, we have I cubed is minus I, and so on, and we can simplify and collect terms, and what we get is the series for cosine of x plus I times the series for sin x. That is, e to the ix is cos x plus I sin x. This is Euler's identity, one of the most remarkable equations in the whole of mathematics, beautifully connecting these seemingly unrelated functions. Well, Euler gave more than one proof of his identity. Here's part of a different approach in which he made use of infinitesimals. This is the proof that appeared in the Introductio, writing the square root of minus 1 instead of I, a symbol he didn't start to use till later. So if you look at the penultimate line, you see Euler's identity. E to the v times the square root of minus 1, that's e to the iv, is cos v plus square root of minus 1 times sin v, cos v plus I sin v. And as Euler himself commented, from these equations we can understand by how complex exponentials can be expressed by real sines and cosines. Euler's equation has even featured on a Swiss postage stamp. It appears up the left-hand side of the stamp on the left. And while we're in a philatelic frame of mind, on the right is an Irish stamp showing the quaternion equations that Raymond told us about, which Hamilton inscribed on the bridge in Dublin. At this stage, let's see another near miss. by the English mathematician Roger Coates, the first Plumian professor of astronomy in the University of Cambridge. Born in 1682 and dying at the age of only 33, he introduced radian measure for angles for the first time and worked closely with Isaac Newton on the second edition of Principia Mathematica. Around 1712, Coates was investigating the surface area of an ellipsoid. The details are rather complicated, but he managed to find two different expressions for the area involving logarithms and trigonometry, and both involving a certain angle phi. He first proved that the surface area is a certain multiple of log of cos phi plus I sine phi, and he then proved it to be the same multiple of I phi. And equating these, he deduced the identity log of cos plus I sine is I phi, which gives a connection between logarithms and trig functions. If he'd then taken exponentials, he'd have discovered Euler's identity in the form e to the I phi is cos phi plus I sine phi. But he didn't. Another near miss. Euler's identity has many simple yet profound consequences. Here are three of them before we conclude. The most important one follows when you put x equals pi, that's the radian form of 180 degrees, to give e to the I pi is cos pi plus I sine pi, which is minus 1 plus 0i, which is minus 1, or e to the I pi plus 1 equals 0, which is Euler's equation. Although Euler must surely have made this deduction, it doesn't appear explicitly in any of his writings. Next, we note that Euler's identity gives us a one-line proof of de Moivre's theorem, which Raymond mentioned in his lecture. For any number n, cos x plus I sine x to the power n, well, that's e to the ix to the n, which is e to the I nx. Well, e to the I times nx is just cos nx plus I sine nx. But since Euler had used de Moivre's theorem to obtain his identity, the two results are in some sense equivalent. We also note that if in Euler's identity e to the I pi is cos x plus I sine x, we replace x by minus x, we get e to the minus ix is cos minus x plus I sine minus x, and that's cos x minus I sine x. And if you add and subtract those two equations, you get cos x is a half of e to the ix plus e to the minus ix, and sine x is 1 over 2i times e to the ix minus e to the minus ix. And these remarkable results show how, by allowing complex numbers, we can rewrite the standard trig functions in terms of the exponential function. So to end with, what should we call the equation e to the I pi plus 1 equals 0? We've seen how it can be easily deduced from results of Johann Bernoulli and Roger Coates, but that neither of them seems to have done so. Even Euler seems not to have written it down explicitly, and it doesn't appear in any of his publications, though he surely realized that it follows immediately from his identity e to the ix is cos x plus I sine x. In fact, we don't know who first stated the equation explicitly, although it does appear in a French maths journal of 1813 to 1814. But almost everybody nowadays attributes the result to Leonhard Euler, so we're surely justified in naming it Euler's equation to honor the achievements of this truly great mathematical pioneer, a word that describes him so well and which appropriately includes among its letters our 5 constants, pi, I, 0, 1, and E. So may I conclude by inviting you to the Gresham College launch of this forthcoming book to be published by Oxford University Press on the 25th of January. The launch takes place at Barnard's Inn Hall, Gresham College Barnard's Inn Hall in High Holborn on the 15th of February at 6 p.m. And I'll tell you all the stories that I didn't tell you today. Thank you very much.